Hello everyone and welcome in this part 3 of our series on the maximum principle related to the heat equation. Now we speak about another approach one can adopt for the maximum principle. We look from a different perspective. We suppose here to set the IDs omega bounded. Let u is t verifying 20. U is the set of continuous function on omega bar times 0t with t strictly positive. We verify also 21. U is of class C1 with respect to t and of class C2 with respect to x and omega times 0t. And we also verify the condition 22. The partial derivative of u with respect to time minus Laplacian of u is smaller or equal to 0. Now, the theorem 10.6. We suppose we have 20, 21, 22 verified, then we have 23. The maximum of u on omega bar times 0t is equal to the maximum of u on p, with p equals omega bar times 0 times gamma times 0t. P is the parabolic boundary of the cylinder omega times 0t. For the proof, we set vxt equals uxt plus epsilon square norm of x with epsilon strictly positive, such as x equals x1 up to xn, with the norm of x equals the square root of the sum from y equals 1 to n of the xy squared. So the norm squared of x is then equal to the sum from y equals 1 to n of the xy squared. We then obtain the gradient of the squared norm, which is simply for each coordinate 2x, 2xy, which leads to the obtention of the Laplacian of the squared norm. We will simply have a sum of 2 leading to the Laplacian of the squared norm of x equals 2n. So we have then 24, the blue framed inequality. How do we obtain this? We have this inequality on omega times 0t. How do we obtain this? Because the derivative of v with respect to time minus Laplacian v equals the derivative of u minus with respect to t minus Laplacian of u minus epsilon Laplacian of the norm of x squared, which is equal to the partial derivative of u with respect to time minus Laplacian of u minus 2 epsilon n. And by hypothesis, the derivative of u with respect to time minus Laplacian of u is smaller or equal to 0. So the derivative of v with respect to time minus Laplacian of v is smaller or equal to minus 2 epsilon n, strictly smaller than 0. Now we show that the maximum of v on omega bar times 0t equals the maximum of v on p. Let's reason by contradiction. We suppose that the maximum of v on omega bar times 0t equals v x0 t0 with x0 t0 on omega bar times 0t and x0 t0 not belonging in p. So the maximum is supposed to be reached within q, within the cylinder, on omega times 0t with 0 excluded, not on the boundary omega bar times 0 union gamma times 0t. As x0 belongs in omega and t0 strictly greater than 0 smaller or equal to t, we have 25 and 26. because we have that the partial derivative of v with respect to t x0 to 0 equals 0 if t0 is slightly smaller than t, and the derivative of v with respect to time of x0 t0 greater than 0 if t0 equals t. Where do 25 and 26 come from? Let's show that the derivative of v with respect to t x0 t0 is greater or equal to 0 if t0 equals t. By definition of a partial derivative, the partial derivative of v with respect to time in x0 t0 equals the limit when h goes to 0 of vx0 t minus vx0 t minus h over h. If we want that the following definition for our partial derivative, this will not be logical as t is the final time. As vx0t equals maximum of v on omega bar times 0t, since t0 equals t, we know then vx0t minus vx0t minus h is smaller, is bigger, is greater or equal to 0. Then the partial derivative of v with respect to t in x0t equals the limit of vx0t minus vx0t minus h over h when h goes to 0, which is greater or equal to 0. So the partial derivative of v with respect to time in x0 to 0 when t0 equals t is greater or equal to 0. Now let's prove that the partial derivative of v with respect to time to the time t in x0 t0 equals 0 if t0 is strictly smaller than t. Let's set delta t strictly positive such that t0 plus delta t is strictly smaller than t. Then the partial derivative of v with respect to time to t in x0 t0 equals the limit when delta t tends to 0 of vx0 t0 minus vx0 t0 minus delta t over delta t by definition, which is bigger or equal to 0, since vx0 t0 equals the maximum of v or omega bar times 0t. But we have also that the derivative of v with respect to t in x0 t0 equals the limit when delta t goes to 0 of vx0 t0 plus delta t minus vx0 t0 over delta t, which is smaller or equal to 0 for the same reason. So we have then that the partial derivative of v with respect to time to the time in x0 t0 equals 0. Finally, we proved 26. We were shown that the derivative of v with respect to time in x0 t0 is greater or equal to 0 for x0 in omega and t0 strictly greater than 0 and smaller or equal to t. Now let's show that the Laplacian of v in x0 t0 is smaller or equal to 0. The second partial derivative of v with respect to x0, the first coordinate of x0 in x0 t0 is equal to, by definition equal to the limit when delta x goes to 0 of the partial derivative of v with respect to the first coordinate of our vector x0 in x0 plus delta x e1 t0 minus the derivative of v with respect to x01 in x0 minus delta x e1 t0 over 2 delta x, with e1 the vector having only 1 in the first position and 0 everywhere else. So our second partial derivative is then equal to the limit when delta x goes to 0 of vx0 plus delta x e1 t0 minus vx t0 minus vx t0 plus vx0 minus delta x e1 t0 over 2 delta x squared. and we know by definition of we know by hypothesis that because v(x0, 0) is the maximum, that the two following differences in orange are smaller or equal to 0. So we deduce that the second partial derivative with respect to x01 in x0 is smaller or equal to 0. Then we deduce from this, because we can do the same thing for all the second partial derivative with respect to x0 y for each y going from 1 to n, we deduce that each second partial derivative of v with respect to x0 y in x0 is smaller or equal to 0. So we have shown 25. Then when we do the sum, we will have a sum of negative terms. The Laplacian of v in x0 is smaller or equal to 0. Now combining 25 and 26, we obtain that the partial derivative of v with respect to t minus Laplacian of v in x0 is bigger or equal to 0, which contradicts 24. Consequently, the maximum of v on omega bar times 0t equals the maximum of v on p, which is smaller than the maximum of u on p plus epsilon c, where c is defined is by definition the supremum of the square norm of x for x in omega. As u is smaller than v, then the maximum of u is on omega bar times 0t is smaller than the maximum of v on omega bar times 0t, which is also smaller than the maximum of u on p plus epsilon c for all epsilon strictly positive. We deduce this from the previous blue field inequality we just explained. So letting epsilon tends to 0, we have then the maximum of u on omega bar times 0t is smaller or equal to the maximum of u on p, and we know that the maximum of u on p is smaller or equal to the maximum of u on omega bar times 0t, because the maximum on the boundary is smaller than the maximum on all the domain, which is logical. Eventually, we obtain 23. We obtain that the maximum of u on p is equal to the maximum of u on omega bar times 0t. And this is the end of proof, end of this part 3. Don't forget to comment. It's up to you to subscribe, to leave a like. I'm not forcing you. Good exploration, good scrolling. I hope you learned a lot of things today. Goodbye.